Hello and welcome. As I wanted to talk today about simplex symmetry in the final and the penultimate layers of neural network classifiers, which is a project that I've been working on with Weinan E. So we've all seen the pictures of deep neural networks. We've got an input and we've got an output, and in between we've got a bunch of hidden layers, and there are linear maps and nonlinear coordinate-wise maps involved. And for all intents and purposes, the inner workings of neural networks are still big black boxes where we don't quite understand what happens despite recent progress. Now, this topic is something that is looking specifically at the layer before the output and the output layer, and we're going to try and understand a little bit more what is going on, and then possibly in future work try to propagate a little bit back throughout the neural network. So this is based on empirical observations from this article, which posted last year. And we were trying to understand certain empirical observations on a deeper level. Now, the setting that we will consider is classification with cross-entropy loss. So we've got empirical risk or population risk, which looks like this. And the loss function is cross-entropy. The hypothesis class in which we're going to work is a proxy for deep neural networks. Namely, we're looking at functions which can be decomposed as a general map, f of x, and a linear map. So this would be the output of in the penultimate layer, and this would be the final layer after the linear map A. Now, for deep neural network classifiers that were trained by stochastic gradient descent with precisely this kind of loss functional, the following empirical observations were made, namely, 1, f maps all points with the same label to a single value. So in the penultimate layer, all points in the same class will collapse to a single point. The distance between the points corresponding to class I and j did not depend on I and j. The same is true for the scalar product here. And the ith row of A is parallel to the vector that points from the center of mass of all the class outputs to the particular class output. So this is what the authors dubbed neural collapse, and we were curious to see why this happens. Now, let's look first at the final layer, at the output of h of x, and then later on we'll go back one layer by look at the linear map that connects the penultimate to the final layer. So in the final layer, let's now just leave h in some general hypothesis class h and set zi to be the average value that h outputs over the ith class. So of the entire class, we're just looking at the mean, and we are then replacing h by h bar, which is constant on all of the classes and just outputs precisely that mean. And by Jensen's inequality, we see that the cross-entropy loss actually decreases under this replacement. As a corollary, we note that if h is a sufficiently flexible class, for example, if h is the class of measurable functions into a convex compact set, then any minimizer of the risk functional in this hypothesis class maps the class ci to a single point. Now, we note that we need the compactness constraint because cross-entropy loss never becomes 0. So cross-entropy on a whole, on an unconstrained class doesn't have minimizers. But if we limit ourselves to a bounded set, then we do have minimizers and we can make this observation. And so in particular, if we've got a ball of radius r greater than 0 in our case, that's a convex set, compact 2, and we take it with respect to an LP norm, then for every I, there exists a unique minimizer Zi of the essentially cross entropy loss of the class. And Zi is given as a sum where EI is emphasized and all the other directions are treated equally. And the coefficients depend slightly on P, but in particular, if we take P is equal to 2, then we get the vertices of a standard simplex as the best possible outputs for the whole classifier H. And so if H is the hypothesis class of P measurable functions which go from RD into an LP ball, then the unique minimizer maps all points in the same class to one of these vertices. So let's go back to the penultimate layer, and here we consider again a function class where the classifier can be decomposed as A times F, where A is linear and F is very flexible, in our case just measurable. And so we're looking at the case where the output is constrained and then the operator norm of A is constrained. Now then we can show that there exists a unique minimizer in this hypothesis class, which is A times F, where with F outputting values yi, which are constant over the hypothesis class, of the classification classes. These points from the vertices of a regular simplex in a generally much higher dimensional space. And the center of mass of these points is at the origin. We lose some translational freedom because we assume there's norm bound. And finally, A is an isometric embedding of the space which is spanned by y1 through yk into rk. So if we have this flexibility already in the penultimate layer, then the best thing that we can do is already be constant in the penultimate layer, already have this simplex configuration, and then we just shift it over to the output space by an isometric linear map. So if H is very expressive, it is best to collapse all points to the vertices of a standard simplex. And we note that this argument is not related to optimization algorithms. So this is pure energy minimization. So asymptotically, it should be true for an optimization algorithm which discovers minimal geometries. However, we obtain this result under the assumption of norm bounds. And norm bounds are meaningful if it is much easier for a classifier to change the direction than the magnitude of an output. So we need to think whether that applies, for example, for deep neural networks. There seems to be a specific role that Euclidean geometry plays for the penultimate layer result, because LP space in Euclidean space, if I've got this k-1 dimensional space that is spanned by all the outputs of the penultimate layer, then if I've got a Euclidean space, I can rotate that any way I want. If I've got P which is not equal to 2, then there are many, many possible geometries. So Euclidean geometry seems to be important. And we believe that that might have to do with the fact that the optimizer and the initialization are generally compatible with Euclidean geometry. Specifically, the authors used SGD, which is based on the Euclidean inner product. And then the question obviously is, well, this is optimal in a class of measurable functions. So this is optimal in a very, very general hypothesis class, which is specifically a class with terrible generalization properties. So is this a general phenomenon that we can observe, or does this have to do with the fact that the classification problems that we typically study are meaningful and have some structure that neural networks can pick up so that they become expressive enough just on this given data set? So how this result relates to generalization is an open question. For shallow neural networks, we've got some counterexamples. Specifically, we're considering binary classification to avoid vector-valued outputs. So we've got cross-entropy loss, where xi is +1 or -1. So we want to get the right sign of the classifier. And we approximate this by a simpler loss functional where we can actually compute gradient flows more directly. In the first geometry, where we see that neural collapse does not happen, we take an infinite width limit of neural networks. We replace a two-layer neural network with which is given by a finite sum by an infinite wide version and expectation. Then the training of these weights by a gradient flow just corresponds to training the distribution of the weights by a Wasserstein gradient flow. And the functions of this type form a Banach space with a norm, which is essentially a second moment bound. And in this case, we know that under certain conditions, the classifiers converge after renormalization to a maximum margin classifier. The fascinating thing about that is, well, in certain simple cases, we can explicitly compute all these maximum margin classifiers. And if we've got linearly separable linearly separable classes, and the classes contain more than one point, then there exists a continuum of maximum margin classifiers, and they are not constant on the class. So if we have Rey-Lou activation, we do not necessarily expect neural collapse here. The second geometry is much simpler. We've got 3 data points, one on the left, one on the right, and the middle one is its own class. So we've got non-linearly separable data. And then we used an activation function which becomes constant for large arguments so that the inner layer doesn't really move. And under those conditions, we can explicitly solve the gradient flow. We've looked at an initialization which has this left neuron only affected by one of the parameters, and the other 2 are both affected by 2. And then we can solve this gradient flow equation, where here we see the interaction between A2, A3 parameters, and here the neuron that is only affected by one of the neurons. And when we solve this, we see that in the limit for a long time, the difference of the output at the right neuron in the class 1 and the left neuron, the left data point, which are both in the same class, tends to this value, which is given where the P3 and P1 are the probabilities of the individual points. And this is independently of how exactly we initialize this. So in shallow neural networks, we see that neural collapse may not happen dynamically, even in the output layer, and even if it is in principle expressive enough to allow neural collapse. There are 2 geometries which seem to prevent that. One of them is if the hypothesis classes are not linearly separable. And the other one is if they are linearly separable, but the activation function is Rey-Lou, then we don't see us becoming constant on these classes in the output. So in deep learning, if the classes are not geometrically nice 2 layers before the output, then they do not collapse in the output layer either. And especially when using a pre-trained model and we just add a few layers, then it is important to wonder whether we actually do see neural collapse. There are similar works with comparable results by Mixon, Parshall, Pai, and Lou Steinerberger. And I think the big question that we need to study in the future in this direction is how the data becomes more separable as it propagates through the layers of a DNN, because we see that it has to be reasonably separable already a few layers before the output in order to show neural collapse. And with that, I would like to thank you for your attention.